Okay, yes, correct. Good. Okay, yeah, the recording is still. Okay, so we can start now. Yeah. So yesterday we saw hyperdeck graph is a perfect matching or not, and that graph, that algorithm relied on the isolation lemma, right? And so like we saw the proof of that algorithm, but we did not see the proof of the isolation lemma. So today we'll first prove the isolation lemma, then look at an algorithm for checking the equality of two strings and then the equality of two sets. Okay. So let's first, yeah, but like before that, but do you have any questions about what we covered yesterday?
No, that was clear too.
Yeah. Okay. So then let's recall the isolation lemma. So the isolation lemma is about a set system U comma F. So what's a set system? A set system is a tuple U comma F. Uh, it U, and let's assume that the universe script F, which is equal to S1 to SM, and all of these SIs are subsets of U. Okay. So this is just a collection of a set and some of its subset. Says that if U comma F is a set system with size of U equals N, and we associate weights W x1 to Wxn with the elements x1 to xn, and define the weight function from 2 to the U to Z. So the weight function is defined for every element of 2 to the U, that is for every element of the power set. So the weight function assigns a weight to every subset of U. Okay. And yeah, so we define the weight function as follows. So W, the weight of S is just the sum over all x in S of the weight of X. Then for any subset W of Z, probability that Wx1 to Wxn picked uniformly at random from capital W, there exists a unique S in F such that weight of S is minimum is at least 1 minus n over size of W. Okay. So this is the statement of the. And over here, like one of the interesting things is that, okay, the family F can have m elements, but this probability does not depend in the universe and the size of the set from which you sample the weights. Okay.
Yeah, can you explain the isolation lemma again? Because I see here a different format of the isolation lemma. The isolation lemma, which was discussed in the computational complexity course, was, if I remember, that was a bit easier, right? So that lemma only talked about the existence of a unique, the probability of getting the unique minimum weight, if I remember. And here something else is happening, at least notation wise. This seems to be slightly difficult to me.
Okay. So are you
uh,
with
I,
perfect matching?
I could not hear you. I mean, your video got freezed for some time. Yeah.
Oh, so I was asking unique minimum perfect matchings.
Again, I could not hear you. I could only hear till the point when you said that, am I comfortable with the perfect matching you discussed yesterday or not?
Oh, no, no, no. Okay, no. So what I was saying is, are you saying that the version of isolation lemma that you are familiar with only talks about unique minimum perfect matching?
No, not about the perfect matching, if I remember. So that used to be something like, say, if we consider if we consider the subsets of a set, and if I assign weights to the different elements of the subsets, then the subset and which carries the unique minimum weight So its probability would be less than or equals to say n by something, n by capital N, if I remember, wherein we were assigning weights to the different elements of the subset ranging from 1 to the capital N, and the set was comprises of say small n number of the elements, and the possible weights which we can assign to the different elements ranges from 1 to the capital N. Then the probability of having a subset of the unique weight, I mean, used to be less than or equals to the small n and divided by the capital N, and probably
Wait, it
it did
can't be
not.
less than or equals to, right?
Okay, I do not. I
The
vaguely
probability
remember
of
that.
not having a unique set would be less than equals to
Yes,
n.
yes, yes. But then,
Yeah.
so in that lemma, usually, I mean, there was no terms like say u and f. I mean, a set system, number one, and second one, the weight function which you have assigned here, like say 2 raised to the power u, assigns to the z. I mean, this is making the things
Okay.
slightly difficult to understand. So if you can explain this isolation lemma again, then that would be easier for me to understand.
Okay. So even over there, the same thing was happening. So you had a set U and you were assigning weights to the elements in the elements in U, right?
Yes, yes, yes. So
So
U is the
all
set, and what this F is
sub
the set of the
F is
subsets. I
just a
guess.
collection of subsets of U. So over there, F was equals to 2 to the U.
Yes, yes, yes. Oh, I see. Yes, now I
Some
understood this
collection of
thing.
subsets
Yeah,
of U,
yeah.
right? Yeah.
Yes, yes. Now I understood because there would be so the cardinality of F would be equals to 2 raised to the power U, and then we are using the weight function to assign the weight values to the different elements of a subset. And
Hmm.
then we are computing this that the probability of there exist a unique minimum is greater than or equals to 1 minus n by w. Oh, yes, I understood this thing now. Yeah, this is, I mean, notation wise, it was slightly difficult. Otherwise, this is one and the same thing. Yeah, thanks.
Yes. Yeah. And so over there, you were picking from 1 to n, but
Yes,
there is
yes,
nothing
yes.
special about this set. Any set of size capital N would work.
Yes, yes, yes. Yeah.
Yeah. Okay. So like, okay. Why am I getting this? Yeah. Okay. So before we move on to a proof of this, let me just give you some intuition about what would happen in the proof. Okay. So I want to prove that the probability that there exists a unique minimum weight, what I can do is I can upper bound that there is no unique set with minimum weights. That is, I can upper bound the probability of there being two sets with the same weight and this weight being minimum, right?
Yes, yes. There is some
Yeah.
severe, I think, video and the audio issue today.
Okay,
So
so let me try my
yes,
earphones.
if you can change your connection, then if it does not work, then I will also try to change my connection if it works. In case if it can be done at your end.
Yeah. Okay, yeah, so I've changed connection. Let's see this is better. Okay, yeah. Oh wait, why can't you see? Can you see my screen?
No, screen is not visible now.
Okay,
But your voice is, but the audio quality is slightly better.
okay. Can you see? Can you see the screen now?
Yes, I can see. Yeah.
Yeah. So okay, yeah, okay. So I was saying that I want to prove that there exists a unique S in F with minimum weight, right? So one way to prove that that is true with large probability is to show that its negation, the probability of its negation is upper bounded, right? That is to show that there exist two sets S1 and S2. So it is that this event happens with small probability, right?
Yes, so you mean to say that we are proving it by the contradiction? Because again, I could not hear you for some time, but I could make it out that so we would be proving it by the contradiction that let us assume that there exist two sets and which have got the same weight with some probability. Is it like
No,
this?
no, okay, so no, no, so okay, what do we want to prove? We want to prove that there exists a unique set with large probability, right?
Yes, yes,
So this statement is the same as saying that there does not exist a unique weight with minimum. There does not exist a unique set with minimum weight with probability at most n over size of W, right?
yes, yes, yes. Right.
Will prove. Yeah. Okay. And one and S2 with the same weight and this weight is minimum, right?
What did you say? S1 and S2. Better if you write, I mean, whatever you say. So, I mean, the crucial point, if you somehow, if you can, I mean, write it here with the marker, then that would be actually easy with little audio and with the text. I mean, I could
Oh,
make
so
it
like
out.
right now I'm not.
I don't know. So, yes. Can you repeat your
Okay,
statement? I would
so
be able to understand.
okay, so what's the issue? Is the volume very low or what's the issue with the audio?
So the issue is that your video gets freezed for some time, and so the audio, I mean, of that portion, I mean, becomes, I mean, I cannot hear that, and then all of the sudden the voice comes in one go. I mean, whatever you say. So
That is
I
better.
mean, so basically, I am hearing your audio after many small pauses. So.
So like let me turn off the video, see if that's better. Okay.
Yes, and meanwhile, I mean, will you give me 1 minute time if I try? I mean, at my end also, and if I change my connection as well.
Yeah. You can do
Okay.
that.
Yes.
Let me
Yes.
turn it.
So am I audible now?
Yeah, you are audible.
Okay, all right. You please continue. Yeah.
Okay. Yeah. Okay. So I was saying that suppose we have two sets, S1 and S2, both have the same weight, and this weight is minimum, right?
Okay. Okay.
Then what would happen is one of them must have one element which is not present in the other, right?
Yes. Yes.
So what I can do is I can fix the value of every weight, sorry, yeah, every weight other than the weight of that element, and then try to argue that the only way S1 and S2 end up having the same weight is if that the weight of that okay, so this is somewhat similar. Actually, this is exactly similar to what we did for Schwarz-Zippel lemma in the linear case. So when there were multiple variables, but the polynomial was linear. So, like, did you say something? Because I didn't hear.
In case if you are speaking something, I cannot hear you, and I don't know why. What has happened?
Okay, so your voice is breaking. Uh, Hello, can you hear me?
Yes, yes, I can hear you now. Yes.
Yeah.
I'm so sorry
Okay.
for the disturbance. I do not know what is happening, but there are frequent, stops in your conversation. Yeah,
Okay.
but you please continue. Yeah, I'll manage. Somehow I'll
Yeah.
manage. Yeah.
Yeah. Okay. So, yeah. So there must be an element in S1 which is not in S2, right? Or something like that. So what we'll
Yes.
do is we'll fix the weights of every other element
Yes.
random, and then we'll argue. Okay. So this is sort of
Yes.
the overall idea of what's going to happen in the proof. So now, like, let's look at the proof formally. So for all I in n, we would define an event EI as follows. Yeah, so we define n events even to En as follows. So let's parse this. Oh, I should write WT for weights, not WE.
W is instead it should be WS1 and WS2, I guess.
Okay, no, so that is fine because not a problem. Okay, and it's the reason is the following. Okay, so what is this saying? So over here, I am going over all S subset of S which contain Xi. And I am saying that uh, the minimum of the minimum of weights of all such sets is the same as the minimum of weights of all the sets which contain xi. Okay. So is the definition of EI clear?
Yes, but then how can the value of the EI is same as that, whether it doesn't matter whether xi is an element of S or not, and the weight is going to be the same. So what does it mean? Does it mean that so this EI will give you the value of all those sets? I mean, wherein the xi is the element of S and is same as the weight of all those subsets, wherein xi is not the element of the set S. This seems
Okay, no, no.
justifiable because one of the element must differ in between A and B. Is it like this?
Okay, so EI is an event, and this event happens when this condition happens. And what is this condition saying? This condition is saying that the minimum the minimum weight among all among all S not containing S xi is the same as the minimum weight of all S's containing xi. This is when EI happens.
Okay.
Yeah, yeah. And okay, so the first observation is what we just argued. Okay, let me do it like this here. Okay, so uh, this observation says that there does not exist a unique S such that the weight of S is minimum if and only if for some I, EI happens. Okay, so is the statement of the observation fine?
Yes.
Yeah. Okay, so since this is an if and only if statement, we have to prove two directions, right?
Yes.
This one is easy. So can you tell me why this is easy?
So one direction is easy because the reason being that I mean, because this EI is happening, so it shows that there exist two subsets. In one subset, Xi is not the element of S. In the other subset, Xi is the element of S. However, their weights are same. So therefore, there does not exist a unique S. So this direction is easy.
Okay, but so there is just one issue with this. Okay, so EI happening tells you that these two are the same, right?
Yes.
But okay, so let me say that. So okay, over here there would be multiple sets. Over here there would be multiple sets. Let's say that this minimum happens for S1 and this minimum happens. So over here, uh, WTS1 is minimum, and over here WTS2 is minimum. Okay,
Yes.
so okay, you have that these two are minimum and these two are equal. But
Yes.
why does that mean that? Yeah, did you say something?
No.
Yeah. Okay, so WTS1 and WTS1 being are the same and they are minimum. But why does that mean that both of them are unique? Like both of them have minimum weight. So over here, WTS1 is minimum, but it is only minimum among all sets that contain xi, right? Not among all sets.
No, I could not understand this. Why so?
Okay, so let's say over here the minimum is WTS1, right?
Yes.
So my question is, can you say that WTS1 is also minimum among the weights of all S in F? So over here, WTS1 is minimum only among all S in F which contain Xi, right? But what I
Yes.
want to
Yes.
argue is that there are two sets, S1 and S2, which are minimum among all sets in F. So I do have two sets, S1 and S2, but S1 is minimum among all sets in F containing Xi, and S2 is minimum among all sets in S not containing Xi, right? I know that they
Yes.
are the same weight, but from here I somehow want to argue that there exist two sets which have the same weight, this weight and this weight is minimum among all sets in F, right?
Yes. Yes. Yes.
So how do I go from these two sets, S1 and S2, to those two sets?
How would you go from the sets S1 and S2 to?
Okay, so S1 is minimum among all S in F containing Xi, and
Yes.
S2 not containing Xi, right? But
Yes.
what
Yes.
I
Yes.
want is I want to come up with two sets, let me call them S1 prime and S2 prime, such that they have the same weight, and this weight. So there is no condition that S1 contains Xi and S2 does not contain Xi, right?
Yes. Yes.
Okay, so
Yes.
what do I want to prove? I want to prove that there does not exist a unique S in F so that the weight of F is minimum, right? So there must exist two sets, S1 and S2, with the same weight, and this weight must be minimum among all sets in F,
Right.
not
Right.
just among sets that contain Xi and not just among sets that do not contain Xi.
Oh, yes. 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 Yeah.
Yeah. But we only have sets which are minimum. Okay, we only have sets whose weights are minimum among uh, sets containing S xi and not containing xi, right?
Yes. Yes.
Yeah. So this is the only thing that we need to do, right?
Yes.
Okay. So this and uh, okay. So there exists I in n such that if there exists I in n, comma s1, comma s2 in f, such that weight of S1 is equal to weight of S2. Uh, Xi in S1, Xi not in S2, and weight of S1 equal to minimum of okay. So okay, now what I'll do is I'll show that the two sets S1 prime and S2 prime that we were after are actually S1 and S2. Okay. And this would solve our. Okay, so let S be any set in F and either xi is in S or xi is not in S, right? So these two are the only options. Is this fine?
Yes.
Yeah. Okay. So if xi is in S, then what's the weight of S? The weight of S. Why is this true?
Why? Because this S1 is having the minimum weight, so the weight of all other sets would be greater than this.
Okay, so S1 does not have the minimum weight, right? S1 only has the minimum weight among all sets containing xi.
Yes, yes.
But over
So,
here, S also contains xi, right? So S also,
uh, yes.
yeah, so
So,
S1 has the minimum weight among all sets containing xi, right?
yes,
But S also contains xi. So the weight of S1 has to be less than equal or equals to the weight of S, right? Because both of them contain xi, and S1 has the minimum weight among everything containing xi, right?
yes,
Yeah. Otherwise, so let's say xi is not in S and weight of S2, right? Why? Same reason. S2 has the minimum weight among all sets not containing xi, and S is a set not containing xi. So the weight of S must be at least the weight of S2, right?
yes,
Yeah. So now S was any arbitrary set in F, right?
yes.
Therefore, for any yeah, this I can write because I've assumed that S1 EI happens, and so S1 and S2 have the same weight, right? So there are
Yes,
only two possibilities for any set S in F. Either it contains X1, Xi, or does not contain Xi. If it contains Xi, then we have that this is true, but we know that these two are equal. So then this must be greater than equal to this as well, right?
yes, yes,
Similarly, if it does not contain Xi, then this is true, but these two are equal, so it must also be greater than equal to this, right? So
yes,
the weight of S1 and S2 is small. Yeah, so weight of S1. Yeah, so weight of S1 and S2 is the same, and this is minimum among all S in F. So we do not have a unique minimum S, right? Because there are two minimum S's, S1 and S2. So is this fine?
yes,
Yeah. So is this fine?
yes, yes. This is fine.
Yeah. Yeah, so this proves the direction, like this direction. Yeah, this was easy. The only thing that we had to do was somehow go from sets which contain xi and not contain xi to general sets, right? Okay, so now let's look at the other direction. So the other direction is, okay, so now there does not exist a unique S in F, so that weight of S is minimum, right? So So if there does not exist a unique set with minimum weight, there must exist at least two sets with minimum. Okay, then there does not exist a set with the unique minimum weight in F, then there must exist two sets with the minimum weight, right? At least two sets with the minimum weight.
Yes.
So let S1 and S2 be any two such sets. Then, since S1 and S2 are different, there must exist an element I, sorry, there must exist an Xi. I'm using Xi for elements. Yeah, so there must exist an I such that Xi is in S1 but not in S2, or Xi is in S2 but not in S1, right?
Yes.
Yeah, because if every element of
It
S1 was in S2 and every element of S2 was in S1, they
yes.
would be the same set, right?
Yes, because S1 and S2 are different, so this must
Yeah.
hold true.
Yeah, so and I can assume without loss of generality that Xi is in S1 but not S2, right? Why? Because otherwise I would just relabel S1 and S2.
Yes.
Yeah. So now what do I have? Uh, so the weight of S1 and S2 is minimum among all sets in F, right? But weight of S1 okay, so there are two parts to this statement. First, that it's the minimum, and that second is this condition, right? So the weight of S1 is minimum among all sets in F. So it's obviously minimum among all sets in F which contain Xi, right?
Yes.
Because S1 also contains Xi. Similarly, yeah, S2 does not contain Xi, so S2 does belong to this set. And furthermore, the weight of S2 is minimum among all sets in F. So yeah, and so what do we have? We have that there are two sets with the same weight. This weight is minimum. Furthermore, S1 does not contain the Xi, S2 does not contain Xi, and so the event EI has happened, right? So is
Yes.
this fine? Yeah,
Yes, yes, this is fine.
yeah, yeah. So we have showed that e- yeah, the only way that you do not have a unique minimum, uh, you don't have a set with a unique, you don't have a set with unique minimum weight if and only if some of the EIs happen. Now I want to say something about the probability of there not existing such a unique S. So I can just say look at the probability of this thing, right? Because these two are the same.
I could not hear this.
Okay, so what I said was I want to upper bound the probability that there does not exist a unique S in F such that weight of S is minimum, right? But since these two statements are the same, I can hello, can you hear me?
Yes, now I can hear you. Actually, it was a long pause. Uh,
Okay.
yeah, yes, but then
Okay, so
I could understand something out of it. That if EI happens, then it is not necessary that S set is unique. I mean, we can have two different sets, say S1 and S2, and yeah, so having the same weight, that can happen.
what I said was I want to upper bound the probability that there does not exist a unique S in F so that weight of S is minimum, right?
Yes, I understood this, because if you can upper bound this,
Yeah.
then probably you would subtract one out of it. I mean, to get the desired result.
Yes. Yeah. So I want to show that uh, this probability is small, but since there is an if and only if over here, I can as well show that this probability is small, right?
Yes, yes.
Because these two probabilities are equal. So yeah, so it's just the union of this probability, right? Because there exists over here, right?
Yes.
Yeah. And now we know that so what upper bound do we know on this probability?
Uh, so yeah, that I mean, all the probabilities such that both S1 and S2 are are same. So I do not remember that. Do we have any existing results for this? I don't remember.
Yeah, so it's just the union bound, right?
Okay.
So this is the probability of a union of a bunch of events is at most the sum of the
Yes,
individual
yes,
probabilities, right? Yeah,
yes. Right, right, right.
yeah. And okay, so there is okay, so now all I need to do is to upper bound probability of one EI, right?
Yes.
Yeah. So let me write it. Probability. Okay. So what we'll do is the following. Uh, okay. Let me first tell you what we'll do. Okay. So what do I want to show? I want to show that uh, that S that let S1 be the minimum let S1 be the set whose weight is minimum among all subsets of among all sets in F containing Xi, and S2 be the uh, sets in F not containing Xi. Then the probability that these two weights are the same is small, right? Now,
Yes. Yes.
do not contain Xi, right? So suppose I were to fix W1, Wx1 to Wxi minus 1 and Wxi plus 1 to Wxn. That is the weight of every element other than Xi, right?
Yes.
Then S2 would become fixed, right?
Yes, and but the because see, if I assign weights and if there are mod of W number of the possibilities, then this is a natural probability that I would be assigning 1 by mod of the W, I mean weight, to any element,
Yeah, okay,
any
but
element.
okay, so yeah, but over here, that's what we are after, right? What we are after is that let S1 be the minimum among let S1 be the set whose weight is minimum among all weights in among all sets containing Xi. S2 be the set whose weight is minimum among all sets not containing Xi. Then what we want to show is that the probability that the weight of S1 and weight of S2 are the same is 1 over size of W, right? At most.
Okay, okay,
Because
okay.
that is what EI is, right?
Yes, okay.
Yeah, so now what I'm saying is, so okay, right now I haven't fixed any sets. Haven't fixed any weights. So I do not have S1 and S2, right? Because S1 and S2 only become fixed once I fix the weights and calculate the set with the minimum weight, right?
Yes.
Yeah. So let me just first divide F into two parts. One, one part is this, all the sets which contain Xi. Another part is all the sets which do not contain Xi, right?
Yes.
Hello, can you hear me?
Now I can hear you, and it was again a long pause. Yeah.
Okay. Yeah, okay. So what I'm saying is I have divided F into two.
Uh, so since I cannot hear you properly, so it would be okay that uh, if you can write, I mean, whatever you are, I mean, important points, if you write here in the proof, say inside the brackets, then I would be able to understand. Actually, I am observing frequent pauses, but when you write something, so from
Okay.
that writing, I can make it out. Yeah.
In that case, what I can do is I can directly start with the proof. Okay. Yeah. So okay. So my claim is this. S2, which is the set with the minimum weight among all elements not containing xi, is fixed. So is this claim fine? Like, can you tell me why this claim is true?
Yes, so basically we have fixed the weights of all other elements except the weight
Mhm.
xi, except the weight
Right.
xi, and then I pick the set and which has got the minimum weight out of all the possible assignments. So yes, so that is S2.
Yeah, okay, but the question is, why is S2 fixed? So
Uh, I could not hear your question. So you mean to say that why this S2 is fixed?
yeah. So why is
So
S2 fixed? So S2 is the set with the minimum weight, right, among all sets not containing xi. But what is
yes,
the weight of S2? The weight of S2 is the sum of weights of all elements in it, right?
yes, yes, yes,
But I haven't given weights to all the elements. I only given weights to all the elements other than xi, right?
yes,
So why is S2 fixed? So first of all, S2 can only become fixed once the weights of all the elements in, or rather, once the weights of all the sets not containing xi is fixed, right?
yes.
Yeah. So my question is, once I fix the weights of x1 to xn, but not xi, why are the weights of all the sets not containing xi fixed? Or are the weights of all sets not containing xi fixed?
So I could not understand the meaning of the term fixed. How do I view it that we are assigning weights to all the elements except xi, and the probability of assigning, say, a weight to any element is say 1 by the mod of the w, and
Okay, so
after the
right now I'm not
assignment.
talking about probabilities at all.
Okay, yes.
So
So
right
even
now
if
all I'm saying is, yeah.
uh, yeah, so even if we do not
So
talk
what we
in
say,
terms of the, yeah, yeah, please continue. Yeah.
yes, okay, right now all I'm saying is, let's assume that we have somehow fixed the weights of every element other than xi, right?
Yes.
Okay. So now I want to say that S, without looking at what the weight of xi is, I can find out what is the set with the minimum weight among all sets not containing xi.
Yes, so S2 is because the minimum weight, I mean, so I could not understand the meaning of the term fixed as such, but from this definition, it
Okay,
seems
so
that since we, yeah,
by fixed, I mean that I have given them weights.
yes, so
So
once
how
we
are we
assign the
constructing
weight,
the weight function, right?
yes, so once we assign
So
weights
to
to all the
construct the weight,
elements of, yeah,
yeah, all the elements other than xi.
yes.
Yeah, so the question is, once I fix the weights of all the elements other than xi, why is S2 fixed?
So yeah, because I mean we are because S2 is the minimum of all the sets which do not contain all the subsets, minimum of all the subsets wherein xi is not the element. So out of the many weight
Yeah, so
assignments, we pick the one whose weight is the minimum one. So that would be
right, but the
fixed
question is,
in the
why is
sense,
it?
but then yes, now I understood your
Yeah, okay,
question
so
that it could be anything, but then so do we have any lower bound for this or what?
no. Like the lower bound doesn't picture into the question at all. So over here, I haven't fixed the weight of xi, right?
Yes.
So any set that contains xi, its weight is not fixed.
Yes.
So the, but any, okay, look at all the sets over here. They do not contain xi, right? So the only elements they do contain are x1 to xi minus 1 and xi plus 1 to xn, right?
Yes.
So once I fix the weights of those elements, the weight function of every set not containing xi is fixed, right?
Yes.
So the weight of everything over here is fixed, and then I can find the minimum, right?
Yes.
Yeah. So that's why S2 is fixed. So let uh, B be the weight of S2. Okay. So by assigning weights to everything other than xi, S2 became fixed. Now let's look at S1. So my claim is also okay. So he saw that uh, for all the sets not containing xi, once I fix the weight of everything other than xi, their weights become fixed. And so the minimum weight, the set with the minimum weight becomes fixed, right? But now I'm claiming that all the sets over here contain xi. I haven't fixed the weight of xi. And even then, somehow I can find out which set will have the minimum value. So why is this true?
So yeah, superficially I can understand the things, but actually I am unable to understand. So what this fixed term here is. So yeah,
Okay,
if you can
S2 is
rephrase, if
fixed
you can,
means the following. So
yes,
over here, there are okay, so let's look at all the sets in F not containing S, right? Not containing Xi.
so can you write it down somewhere, say so that
Hello.
I mean using the red ink only, can you write it down? Can you give an illustration so that it will be easy for me to understand? But I could superficially I could understand that, but this fixed term is not clear actually.
Okay, so let me look at all the elements in F not containing Xi. So those are the elements that appear over here, right?
Yes.
Okay. By fixed, what do I mean? So like when I haven't assigned weights to any of the elements, any of the set over here can end up with the minimum weight, right? So
Yes.
there are lots of sets over here, but the set with the minimum weight come fixed, right?
Yes.
Yeah. So by fixed, what do I mean? I mean the following. All these elements, their weights are fixed. That is all, pick any S. All the elements in S have been assigned weights. So every xj in S has been given a weight wxj. So the weight of S is fixed because that's the sum of the weights of the elements inside it, right? So
Yes.
once I have the weights of all the elements over here, only then can I find the set with the minimum weight, right?
Yes.
So by fixed, I mean that something has happened, and because of that something, I can now say with surety that among all the sets over here, S2 is the one with the S2 is the one which is going to have the minimum weight, no matter what happens now.
Yes. So this is as per the definition, and therefore
No, no, no,
the
okay, okay, there is no
S1.
definition over here. So S2 is defined as this. So,
Yes,
okay, but
S2 is
when does this
defined like this.
definition make sense? This definition only makes sense when I have enough information to find out what which set would have the minimum weight, right?
Yes. Yes. That's true. That's true.
Right. Yeah. So my claim is once I fix the with surety which set over here would have the minimum weight. Why? Because let's look at any set over here. it does not contain xi, right?
Yes.
So once I fix the weights of x1 to xi minus 1 and xi plus 1 to xn, the weights of all the elements in that set are fixed.
Yes.
So the weight of that set is fixed.
Yes. Yes.
Yeah. And since the weights of all the sets are fixed, I just have to pick the set with, I have to pick any set with a minimum weight, and that is my S2. That is what I mean by fixed. So yeah, by fixed, I mean that once this has happened, I can say which short, I can look at all the sets which do not contain S, Xi, and point to one set which is going to have the minimum weight. That's what I mean by fixed. So is this fine?
Yes, this is fine, and therefore, so I could make it out that the S1 is also fixed in the sense that now we would be considering all the sets wherein Xi is appearing. So,
Right.
yes, so once so I mean, so then we would be as I mean, so then out of the many possibilities, we will pick the one whose weight is minimum. So that is also fixed. So that is, I
Okay, no,
mean,
no,
that is according
okay,
to
no,
this
no, no, no.
statement.
Okay, so this argument doesn't work. Why?
Okay.
Because okay, let me look at any set in which contains Xi, right? Because
Yes.
because I haven't assigned a weight to Xi, the weight of that set is not fixed. Okay, so let's say S is X1 and Xi. So I have given weight to Xi, but I have given weight to X1, but I haven't given weight to Xi yet, right? So what's the weight of S? The weight of S is Wx1 plus Wxi, but I haven't fixed Wxi. So the weight of S is not fixed yet, right?
Yes.
Yeah, so in fact, this happens for every set over here. So for none of the sets over here is their weight fixed. But my
Yes.
claim is, despite this, I can still look at all the sets and say that regardless of what weight I pick for Xi, this is the set with the minimum weight. And that is going to be S1. Okay.
Yes. Yes.
So my question is, why is this true?
Yes, so now I understood that. So whichever weight I assign to the element xi, and still I would be able to
Hmm.
fix the value of the s1. Because I would be having the limited possibilities of the weights which I could assign to the element xi. There would be finite number of the possibilities. So
Okay.
then, I shall.
But it is
So then
possible,
I
right,
shall.
that for every possibility, I might get a different S1.
Yes, so I may get it different, but then if the sum of the weights of the remaining element is too low, that even if I assign the highest value of the weight to the element xi, uh, so yes, so I will do one thing, that I will assign the highest value of the weight to the element xi, and after
Okay.
assigning
So
the
right now
highest
we are
value,
not doing anything like that. Okay. So WX1 to WXN are arbitrary. We haven't said that this is the smallest or this is the largest. All I am saying is once I fix WX1 to WXI minus 1 and WXI plus 1 to WXN,
yes.
even without looking at WXI, I can figure out what S1 is going to be. So which set will have the minimum weight among all sets containing Xi.
Oh, so that is not clear to me. Yes, but then
Okay. So let's look at any set over here, right? So what does it
yes.
what would its weight be? Its weight
So
would be
it's
the weight of Xi plus the weight
yes.
of some other elements other than Xi, right?
Right, right, right.
But this thing has been fixed.
Yes,
So now its weight can only be this number plus Wxi, right?
yes,
So let me look at two such sets. This would be their final weights, right?
yes,
So if this number is smaller than this number, then this must be the minimum, regardless of the value of Wxi.
Right, that's true. I mean, that's true. And following the common sense, yes, makes sense.
Yeah, so basically what's happening over here is the following. Once I have fixed every weight other than the weight of x1,
Hmm.
the only possibility, okay, the weight function is almost complete. Every element over here then looks like, let's say, B of S, okay, A of S plus Wxi. So this is what the weight of everything over here would look like. And to compare, okay, so now I want to find the one with the minimum weight. This is the same in everything, right? So the one with the minimum weight must have the minimum AS, right?
Yes.
Yeah. So even though I haven't fixed the weight of x1, s1 is fixed. So is this fine now? No. Did you say something? I didn't hear you.
Yes, yes. This
Yeah.
this is clear to me. This is clear to me. Yeah.
Yeah. Yeah. So we have so just by fixing the weights of everything else, the weight of S1 and S2 became fixed. Now, okay, so let yeah, so I haven't fixed this yet, but this is fixed, right?
Yes.
Yeah. Okay, so now what do I want to avoid? I want to avoid weight of S1 and weight of S2 becoming the same, right?
I want to avoid the weight of. Uh, I want the
Okay,
weight of the. I want
yeah,
the
yeah,
weight of
to be the
S1
same,
and S2
right?
to be same.
Yes, given. Yeah, but I cannot write this. I need to only say that this is over X because I S1 and S2 after fixing the weights of everything else, right? So what's the weight of S1? This is uh, WXI equals B. Yeah, so this probability is the same as this, right?
Yes.
And what is the probability of this happening?
Okay. So. Uh, So the weight of S1, and given that this xi minus 1 xi and then w xn, so that is the probability of, so we are picking the value of any xi. Yes.
Okay, this uh, so this is a polynomial in WXI with just one variable, right? Sorry, with degree one.
Yes. Yes. So I
And
remember
I'm
that.
picking
Can
WXI
can
value.
we, yes, so can we use that, that Schwartz, I mean that lemma,
Yeah, we can use
and
just particle lemma. Yes.
yes, let's say that that would be less than or equals to the d divided by the mod of s thing, and the
Yeah, so
degree is
since
equal
this
to
is
1
an
here and s is this one. Yeah.
but I have only upper bounded this conditional probability, right? Not the
Yes.
this probability. But that's
Yes.
easy because okay, so this thing is easy because I is equal to probability S1 is this. I'll be right. Okay, so probability of EI is this. But now what I can, oh, I need to take a back class. Yeah, what I can do is I can condition, right?
Yes.
And sum over all. Yeah, so I can do this, right?
Yes, we can do this, and yeah, we can do this. We can do this.
And so
Yeah.
now this is at most 1 over W, size of W.
Mm-hmm.
Well, let me write only there. The first thing is at most 1 over size of W. Second thing remains as it is. Yeah, but this is just, oh, this is at most. Yeah, so I can take this comp. So this sum is just 1. So is this right?
Yes, yes.
Yeah. So over here, we sort of use the same idea that we used to prove the special version of Schwarzschild, but for just degree 1 polynomials, right? By
Yes, yes. Yes, this is similar to that only. I mean, for the
yeah,
polynomials of the degree one.
yeah. Okay, so now we know that each and every one of These is at most 1 over size of W. So this sum is at most N over size of W, right?
Yes.
Yeah. And from observation one, we saw that observation two, we saw that this is exactly the probability that there does not exist a unique S, of there not existing a unique S with minimum weight is at most N over size of W.
Right.
So over here, you are getting 1 over size of W from the fact that the polynomials involved are linear, and you are getting N from the fact that there will be N such polynomials.
Right.
Yeah. So is this fine?
Yes. Yeah. So I think that we have completed this proof of the isolation lemma, and we have uh, we have covered all I mean observations. So my question here is that
Hmm.
do we find other use cases of the isolation lemma, and other than the this perfect matching and related things, like say what could be the possible use case of knowing this thing, that out of the many subsets of a set, we would be
Hmm.
having a very high chance of having a minimum unique minimum weight to a subset. I mean, this fact can be used elsewhere.
So I haven't come across any application of isolation lemma other than the MVB algorithm and like the variants of MVB algorithm for general graphs. So MVB is only
Okay.
for bipartite graphs. You can only have MVB for like something like MVB for general graphs.
Hmm.
But yeah, perfect matchings are the only applications of isolation lemma that I have found. So that I know of.
Okay.
Yeah.
Okay, but then I mean, so is this fact so very interesting and so very profound? I mean, even from the common sense also, I mean, except quantifying the result, even from the common sense
Hmm.
also, I could understand that if I consider a large number of the possibilities of the subset, say 2 raised to the power n, and if I randomly assign weights to the different
Hmm.
elements of the subsets, then there would be a very high chance that I would be able to find a subset having the unique minimum weight.
Okay.
So,
So yeah, the like intuitively it makes sense. The only issue is quantifying, right? So the question. So the interesting thing about isolation lemma is that it shows you that this quantity does not depend on the number of subsets.
oh, I
It is
see. Yes,
completely independent of the number of subsets. Yeah.
yes,
And
yes.
okay,
That is.
let's see why this is important. Because let's look at the perfect matching thing, right? How many
Yes.
perfect matches can a bipartite graph have?
I do not know the exact number, but so perfect matching could be, I mean, the so in the bi-adjacency matrix, I mean, all the rows should get covered, and in every column we
Hmm.
should get exactly one.
Right.
So but then I do not remember a result wherein the maximum number of the perfect matching is given for a given graph, for a given bipartite graph.
Okay. So it's n, the maximum number is n factorial. Why? Because in the worst case, the graph can be completely connected and every vertex in L can be matched to every vertex in R, right?
Yes, yes, yes.
So in the worst case, I have n factorially many perfect matchings,
Hmm.
right? And remember that to find okay, checking a perfect matching was fine, but to find a perfect matching, we crucially require you do not have that unique minimum weight thing. You would end up finding edges from multiple. You would end up adding edges from multiple perfect matchings to your output, right?
Yes, yes.
Right. So there are n vectorially perfect matchings, and if this probability depended on m, then this probability, let's say this was m over size of w, then size of W would have had to be huge, right?
Yes, yes.
Yeah. So what isolation lemma does is it tells you that this does not depend on M. So even in the case of perfect matchings, you only need to worry about how many vertices are there. So the
Yeah.
main contribution of isolation lemma is to give this exact quantity bound, which is independent of the size of
Independent of the size of?
F, this set F.
Yes, independent of the size of the possible number of the subsets.
Right, yes.
Yes, yes, yes.
Yeah,
That makes sense.
yeah.
Yeah.
Because
And probably
if,
that is why
let's say the
this that
size
is
of W had to be something like 2m, that is 2 to the 2 times n factorial, then you would need log 2n factorial many random bits, right? And
yes.
log to the n factorial is n log n. So to just pick the random bits, you would need linear time. So yesterday we said that MBB gave a parallel algorithm which ran in time order n square, right?
Yes. N log square n. Yeah.
Right.
Yes, yes. Log square n. Right.
Yeah. But if to pick a, then your running time would even in parallel, your running time would end up being order n log n, right?
Yes.
So you won't get a parallel algorithm with good efficiency. So can you hear me?
Yes, I can hear you now. And again, it
Yeah.
was slightly, yes,
Okay.
that you was.
Yeah.
But I could understand, and probably because of this thing, I mean, we call this an isolation lemma. Is this the reason
Yeah.
behind this
Because it
isolation thing?
isolates the unique minimum weight.
Yes, yes,
Yeah.
yes.
Okay, so now we have just 3 minutes. Okay, so one thing I can do is the following. So I wanted to cover like algorithm using Schwarzschild for checking that two sets are equal. But what we can do is I can like add this as a question which we would solve in the problem solving session. All
Okay,
you have to
okay,
do here is come up with two polynomials for S1 and S2. So what you can do, okay, so I can explain the problem to you and you can think about it. Okay.
okay, okay.
Yeah. So the problem is the following. I have two sets, S1 and S2. Okay, so these are sets. So they are collection of elements, but the collection is not ordered, right? So for example, A, B, C is the same as C, B, A, right?
Mm-hmm.
Okay, so I have been given two sets, S1 and S2, and I want to check that these are the same.
Mm-hmm.
So can you think of a okay, so the deterministic algorithm is simple, right? Go over every element of S1. For every element of S1, go over S2 entirely and check if this element appears in S2 or not, right? If it appears,
Yes,
remove it.
yes, yes. So for every element, I'll have to make say n. I mean, I would be requiring one scan and requiring time of the order of n.
Right.
And say if there are n number of
Yeah.
the elements in the set S1, then I
Right.
would be requiring an effort of the order of n square,
Yes.
deterministic thing. Yeah.
Yeah. So I can quickly write the deterministic algorithm.
But this problem is very interesting. Why? Because this set is an unordered collection. So I cannot
Right.
think of
Yeah.
anything similar to the binary search kind of the thing. Yeah.
Yes. Yeah. So the running time is So now the goal is to come up with a randomized algorithm whose running time is much smaller. In fact, the running time would be what? That polynomial, I can evaluate order in time. Yeah. So the goal is to come up with a randomized algorithm whose running time is order n. And we would use Schwarzschild to do this. So yeah, recall that general recipe for using Schwarzschild, right? I have to come up with a polynomial which is non-zero, or sorry, which is zero if and only the two sets are the same, right?
Yes, yes, right.
Yeah, so in fact, what would happen is, in this case, you would come up with two polynomials, P1 and P2, such that
Mhm.
P1 would be derived from S1, P2 from S2, and P1 and P2 would be the same if and only if S1 and S2 are the same. Okay.
Yes, yes,
Yeah, so now the question is, can you come up with such P1 and P2? Yeah, that's the question. Okay.
yes,
So,
yes.
okay, let me write this.
So that later on, I mean, we would be able to show that with what probability this P1 minus P2 is equals to a zero. Uh,
Right.
and
That would depend on how large a set you sample from, right? Sample your random points from.
yes,
Yeah, because we
and
would
then
use
we
Schwarzschild, and in Schwarzschild there is the size of S. Yeah.
yes, and then you would be repeating, I mean, that experiment polynomial number of the times so as to get
Yes. Yeah.
something. Yeah. So I was looking for this recipe in your lecture notes. So last time we discussed that if you can draw or if you can suggest some resource wherein a flow chart is given or some recipes given to, I mean, because I could understand the pattern
Oh, so
in
I
the
think I
sol
wrote this down
in the
somewhere.
problems we solved.
Oh, so yeah, it's here. So
Okay.
yeah, so from the page in which there is this same, it's two pages after
Yes.
that.
Okay. Okay. Yeah.
So
Thanks.
okay, yeah, okay, the last page before lecture begins.
Okay. Okay. Yes.
Yeah. Okay, so okay, yeah, okay, let's end the meeting today. So next Friday we are meeting from 5 to 6, 7:30, right?
Yes. Yes. Yes.
Yeah, so from 5 to 6:30 we would talk about the Miller-Rabin primality test,
Yes.
and from 6:30 to 7:30 we'll like have a problem solving session. Yeah.
Yes. Yes. Yes.
Yeah, so one of the problems would be this, another was so like I have, yeah, another is this. Yeah. So basically all the problems which are marked question in the,
Yes. I will go through these problems. Yeah.
yeah, okay.
Thank you so very much. And yeah, even though today's session was, I mean, so very disturbed because of the
Yeah,
audio issues, but still I could understand most of the things. Thank you. Thank you so very
yeah,
much.
yeah. Thanks. Bye.
Yeah. Bye. Bye.
Let me stop that recording.